Example number 2, solve the differential equation using Laplace transform d squared x over dt squared plus 2 dx over dt plus 5x is equals to 0. So this is an homogeneous ordinary differential equation given that when t is 0, x is equals to 0 and dx over dt is equals to 1. So the first thing is to get the Laplace transforms, is to write down the Laplace transform of these derivatives, isn't it? So you start, before you write the Laplace transform of the derivatives, you need to exploit the boundary conditions. Does not matter what you start with. Let's just deal with that first case. We start by getting the Laplace transform of those derivatives, isn't it? So you know very well that the Laplace transform of dy dx, this is dx over dt, is given by what? As Laplace transform of x minus x of 0. Remember, we had that the Laplace transform of dy over dx. This is what we had, isn't it? So Laplace transform of dy over dx was as Laplace transform of y minus y of 0, isn't it? But now that means where there is y, you put x. Where there is y, you put x. Where there is x, you put t, isn't it? So that is what it means. So it means Laplace transform of dx over dt, where there is y, you put x. And that is what we have, isn't it? You track it with what you know, isn't it? Then after that, we found that the Laplace transform of d squared x over dt squared, you square this, isn't it? You multiply this with s, then you add, then you subtract the first derivative, isn't it? So that is what you are doing. You multiply it all through there by s, isn't it? So it is going to be s squared, isn't it? Laplace transform of x minus s, isn't it? S, x of 0. Then now you subtract the first derivative of x. Are you seeing that? So it is simple to master. Meaning once you've mastered this, the other one you simply multiply all through by s. Are you seeing? So you have s squared Laplace of x minus s, x of 0. Then you add, subtract the first derivative, isn't it? Are we together there? Good. Now after that, you now come and you exploit the boundary conditions, then you substitute them here. You know, we've not started solving the question. Are you seeing that? We are still substituting. So we have to solve this boundary condition. We are differentiating x with respect to t. Are you seeing that? So if you are differentiating x with respect to t, it means x is a function of t. Are we together? So it means, what is the value of x when t is 0? You can see where there is t, you put 0. Meaning when t is 0, x is what? X is 0. So have you seen you join this and this? By definition, isn't it? Meaning x is a function of t. So where there is t, if you put 0, what is the value of x when this t is 0? Isn't it? So when this t is 0, x is 0. You form the first equation. So that first equation, you are going to substitute it where you have x of 0, isn't it? Are we together? Then the second one you do again, the first derivative, isn't it? If you differentiate this for the first time, meaning x prime is x prime of t, isn't it? Which is that last one, isn't it? Meaning, when t is 0, the first derivative is what? Is 1. Are you seeing that? You've joined this and that, isn't it? The first derivative dx with respect to t is this, isn't it? So when this value of t is 0, what is this? It is given to be 1. Are we together? So where it is, where you have f prime of 0, x prime of 0, which is this part, you are going to substitute 1. Are we together? So after getting that, now come back, what is now the Laplace transform of dx over dt? Now substitute, where there is x of 0, you put x of 0, which is 0. Are you seeing that? And where there is Laplace transform, that is what we are looking for, isn't it? The Laplace transform of x is what we are looking for in the problem, isn't it? So if you substitute x of 0, which you found to be 0, you remain with this to be as Laplace transform of x only. This will be 0, isn't it? See, you are done with that. You move to the second one is the Laplace transform of d squared x over dt over dt squared, isn't it? The Laplace transform of d squared x over dt squared to be, it is what? It is s squared Laplace transform of x, then it is minus s x of 0. But what is x of 0? Meaning the whole of this goes to 0, isn't it? Then it is minus x prime of 0. And what have you found x prime of 0? So it is minus 1, isn't it? So you found the simplest form of this and this, isn't it? Are we together? Now, having done that, we now go back to our equation, isn't it? What is our equation? Our equation is d squared over x over dt squared plus 2dx over dt plus 5x is equals to 0. Meaning we introduce Laplace on both sides of the equation, isn't it? So if you introduce Laplace on both sides of the equation, what do you have? You will have Laplace transform of dx over dt squared, then it is plus 2. 2 is a constant you factor outside, isn't it? So it is plus 2 into Laplace transform of what? Of dx over dt, then plus 5 Laplace transform of what? Plus 5 Laplace transform of x. You must introduce Laplace on both sides of the equation. When you have an equation, you can do anything on both sides of the equation, isn't it? Then it's equals to Laplace transform of 0. But Laplace transform of a constant is just 0. Are we together? Laplace transform of 0 is 0. So from here you start substituting. What is the Laplace transform of this second derivative? You found it here, isn't it? It is s squared. You found it to be s squared Laplace transform of x minus 1, isn't it? You bracket it because the whole of this means that, isn't it? Then it is plus 2 Laplace transform of dx over dt. What have you found it? S Laplace transform of x, isn't it? Then it is plus 5 Laplace transform of x to be equals to 0. Are you seeing that? So the next step is to open the bracket, isn't it? The next step is to open the bracket. So if you open this bracket, you will get just the way it is. S squared Laplace transform of x minus 1. Then this other one, 2 times s, you get plus 2s, isn't it? Laplace transform of x, isn't it? Are we together? Laplace transform of x. This minus 1 is here. Plus 2s Laplace transform of x, then plus 5 Laplace transform of x to be equals to 0. So the next thing is to remove any term which does not have Laplace of x, because this Laplace of x is what we are looking for. We are looking for the solution of x, because x is a function of t, meaning our final answer should be x to be equals to something, isn't it? Because x is the dependent variable, isn't it? Are we together? So it means only Laplace transform of x terms with Laplace transform of x is what should be left on the left hand side of that equation. Any term without Laplace transform of x should go on the right hand side of the equation, isn't it? So you start, this term here is having Laplace transform of x, so it is s squared Laplace transform of x. Negative 1 goes to the other side because it doesn't have this, isn't it? So it means you collected this. The next one is plus 2s Laplace transform of x, then plus 5 Laplace transform of x. This one. Are we here? We are here, okay? To be equals to, you've collected that. So what is left? What is left is this negative 1, isn't it? Negative 1 going on the other side of the equation, it becomes positive 1. Then now, you factor out the common factor, isn't it? The common factor is Laplace transform of x, isn't it? So if you factor out the common factor, Laplace transform of x, here you remain with, if you factor it out here, you remain with s squared, then here you remain with plus, then here you remain with plus 5 to be equals to 1, isn't it? So for you to get Laplace transform of x, you must get rid of its coefficient, isn't it? Meaning you divide both sides of the equation by s squared plus 2s plus 5. You divide both sides of the equation by s squared plus 2s plus 5. So this cancels with that, isn't it? So you remain with Laplace transform of x to be equals to 1 over s squared plus 2s plus 5. Are we together there? So after you found that, it means for you to get x, you take Laplace on the other side of the equation, isn't it? And when you take Laplace the other side of the equation, it becomes Laplace inverse, isn't it? So before you take it to the other side of the equation, this, what is on the right hand side of the equation, must be in a standard form such that you are able to get back that function you transformed, isn't it? So this one, the first thing you check, are you able to use partial fraction? Are you able to factorize it, isn't it? If you're not able to factorize it, then you complete the square. Are you getting that? So you just check the factorization method. If factorization method does not want to use completing square, but you can use either, but in order without sums, isn't it? The reason being, even if you are doing integration, see this comes a case when you are getting your answer to be in form of the Napier logarithm ln, and somebody else is getting the answer to be an inverse function or sec inverse of something, isn't it? Why? Because even inverse function can be expressed in logarithmic form. Are you seeing that? So that is the reason why we are saying, if you complete the square, you can maybe get an answer in form of something. If you resolve into partial fraction, you can also get the answer in another different form, isn't it? But now if you have the boundary conditions, and then you find the answers are just the same, isn't it? Are we together? Because functions can always be transformed. Exponential functions can be transformed into trigonometric function. Exponential function can be transformed into hyperbolic functions. Therefore, inverse function can be written in logarithmic form. So it doesn't matter. If you're not able to complete this, if you're not able to factorize, you complete the square. Completing square is the simplest, isn't it? Instead of factorization. So completing square is the simplest instead of partial fractions. Are you getting that? And partial fraction, you only resolve into partial fractions if you are able to factorize this. Are we together? So if you look at this, here A is 1, B is positive 2, C is 5, isn't it? So which numbers gives you a product of 5 and a sum of 2? They are not there, isn't it? Meaning you cannot use factorization method, isn't it? So if you cannot use factorization method, meaning you complete the square. Are we together? You complete the square. Now completing the square is very simple. This is what you do. You go and this is what you do for you to complete this square. What do we want to complete this square? You go to your rough work with this term you want to complete this square, isn't it? You write it aside. You have it is s squared plus 2s plus 5. We want to complete it square, then we take it back to our problem, okay? Are we together? So if you want to complete a square, you must always know that this term must not have a coefficient, but here we are lucky, it does not have a coefficient, isn't it? Are we together? Then after that, you get rid of the constant term, isn't it? This is not an equation, meaning this is an expression, so you have to deal with it as an expression because it is not equated to anything, isn't it? So you get rid of the constant term, meaning what you do, you put s squared plus 2s, then you close the bracket, then outside the bracket plus 5. So it means you've gotten rid of the constant term. So you want to add the constant term of this complete square. Are you getting that? Okay? After doing that, you now move. If you have to add the constant term of a perfect square like that. You have to add the constant term of a perfect square. If you add something inside the bracket, because this is what? Look here. This is an expression, isn't it? So if you add something here, meaning you must subtract the same thing you added to balance it, isn't it? Meaning if I had 5x plus 2, if I add 3, I have to subtract that same 3 I've subtracted for it to remain the way it was, isn't it? But I'm doing that because I want to complete this square, isn't it? So what are you adding here? This square term. This square term you're adding must be a half the coefficient of the middle term, isn't it? So a half of positive 2 is positive 1. So if you added positive 1 here, meaning you must also subtract that positive 1 the other side. You must subtract it to balance it here. So you see, plus 1 squared and minus into 1 squared will go back to 0. Meaning you are only doing that to complete the square. Are you seeing that? And the constant term of a perfect square must be added. So it means outside the bracket is where you subtract it. Inside you must add it, isn't it? Are you seeing that? Then you now start collecting. Here, what do you have inside this bracket? You collect the square term. The square term is s and positive 1. So it is s and positive 1 all squared. Are you see? So you can remove this outer big bracket because you now added the 2. Meaning if you expand this, you get back the problem, isn't it? So this sign here in the middle is very important. Meaning if it was minus 2, meaning inside that bracket you are going to write negative 1 because that sign here is very important here. Are you seeing that? Are we together? Then outside the bracket, what do we have? we had here is plus 5, then minus positive 1 squared is just 1. Are we together? So after doing that, so you just use a calculator to join those ones which are outside. Isn't it? So what do you have? S plus 1 squared, then plus 5 minus 1, you get a total of plus. And you know in Laplace transform, in the denominator, we always have s squared plus a squared, isn't it? Meaning this form, you must look for its square root and square it to be in form of a squared, isn't it? So that square root of 4 is 2, so it means 4 can be written as 2 squared. So it means where you have s squared plus 2s plus 5, you are going to put that. Are we together? Because that is what is going to give you a standard form of transforming any function into Laplace. Is that okay? So can you now go back here to your problem? Where there is s squared plus 2s plus 5, you put what you found. What have you found? What have you found? You found it is s plus 1 squared, then plus 2 squared. So you know in the denominator, you know very well when you add s squared plus a squared, this was always trigonometric. It is either cos or sine, isn't it? So that will depend with what is in the numerator. If what is in the numerator is a constant, it is sine, isn't it? When what is in the numerator is s, it is cos. But when it is s minus or plus something, you know it is a product with the exponential function, isn't it? So you can see here it is x plus 1, meaning that is a product with the exponential function. So let us go back to our problem. Laplace transform of x. Laplace transform of x is equals to 1 over this term which we've completed the square. What have we found? We found s plus 1 squared plus 2 squared, isn't it? Then one thing you know is that when you have s squared plus a squared and the positive sign here in the denominator, you know that is automatically trigonometric, isn't it? So you will go back and you recall that the Laplace transform, there is no s in the numerator, so it is sine. Because cos is what you have the posted rule s over, isn't it? So sine is always, if you have Laplace transform of sine at, you know it is a over s squared plus, when it is sine, isn't it? So because here you have s plus 1, meaning it is a product with the exponential function. Are you seeing that? So if it is a product with the exponential function, then this your a, you let it to be w. So if you let that your a to be w, so we have sin wt. So the moment you are now looking for the Laplace transform of exponential at, because this constant in exponential and this constant in sin are different, that's why we are choosing a different value and leaving a for exponential, because exponential is going to be joined by the definition of Laplace. Exponential at is going to be joined by exponential negative st, isn't it? That's why we are letting the exponential to have a, so this one we now change it to be w, isn't it? So if you have the Laplace transform of exponential at sin wt, you know that where there is s, you are now going to have s minus a, isn't it? Only where there is s, isn't it? You are going to have s minus a. So it means here w is not affected, it remains the way it is. Where there is s, because you know in Laplace transform form it of f of t exponential minus a st dt, if you substitute your exponential at, it is going to join up, isn't it? So that you have s minus a, isn't it? So here we are going to have where there is this s, it is no longer s because we have exponential at, so it is going to be s minus a squared. W squared remains the way it is, isn't it? Are we together? When it is just in wt, it is just w over a squared plus w plus. In at, it is a over a squared plus a squared. Because we want to put a on top of exponential, we change this to be another variable, okay? Are we together? So after that, you now go back to that your problem after you identified the Laplace transform of a function which applies, isn't it? Meaning if you take Laplace to the other side of the equation, you will find that this side you remain with exponential at sin wt to be Laplace inverse of w over s minus a squared plus w squared. Are we together? Now after you found this, you now put this one aside. You know very well that this is what is applying in what you have. Are we together? You know very well this is what is applying in what you have there. So we go back where we stopped in our problem, isn't it? We stopped here, isn't it? So if this is w squared, you must have w in the numerator, meaning w is this 2, isn't it? So in the numerator, for you to have 2, here is just 1, 1 is just 1. For you to have 2, 2 must be there, meaning you must multiply by a half, isn't it? It's like 2 over 2. Are we together? Because we must have W in the numerator. Are you seeing that? And that W, according to it, is W squared, 2 squared, meaning W is 2. Are you seeing that? So 2 must be in the numerator. And if you put 2 in the numerator, you must multiply by half. It's like it's just 1 in the numerator. There's nothing you've done. But you're doing that to ensure that you have that W in the numerator, isn't it? So after you add W in the numerator, so you now factorize this a half outside. Are we together? So if you factorize that half outside, you remain with Laplace of x is a half into 2 over s plus 1 squared plus 2 squared. So are you seeing now what we have inside the bracket? We now have W over s minus a squared here plus W squared. So what do? You take Laplace the other side of the equation. Is that okay? It becomes the Laplace inverse. So if you take Laplace the other side, it becomes Laplace inverse. Then here you remain with x, isn't it? So you remain with x is equals to Laplace inverse of a half is a constant you factorize out, isn't it? A Laplace inverse of 2 over s plus 1. It is not supposed to be s plus 1. It is supposed to be s minus a, isn't it? So when you have s plus 1, it means it is s minus negative 1 squared, meaning a is negative 1. Are you seeing that? Because it is supposed to be s minus a, but here you have s plus 1, meaning this plus 1 is the same as s minus negative 1. So it means your s minus a is negative 1. Are you seeing that? And not 1, isn't it? So it is that, then it is plus 2 squared. So after that, you just substitute. Where there is W, you put 2. Are you seeing? Where there is W, you put 2, isn't it? And where there is A is negative 1. Is that okay? Is that understood? Yeah, because you can see your W over W squared, 2 over 2 squared, meaning where there is W, you put 2, isn't it? So it means the Laplace our W, if we put 2 where W is, if we put 2 where W is, we get that, isn't it? Then if we put negative 1 where A is minus negative 1, it becomes plus 1, isn't it? Where A is, you put negative 1. So you see, the whole of this problem, Laplace transform of 2 over s minus 1 squared plus 2 squared, the whole of this we found is what? Exponential negative t sine 2. Are you seeing the way we move stepwise? Are we together? Yes, so it is, the whole of this problem you get is x is equals to a half. Laplace transform of this we found is exponential negative t sine wt, but w is 2, isn't it? Sine 2t, exponential at, but a is negative 1, isn't it? So it is exponential negative t sine wt, w is 2. Are we together? And you are done, meaning all those other ones I was just putting on the rough work for explanation. Are we together? And we have solved the ordinary differential equation using Laplace transform. Are we together there? Good.